it is being taken. So here we take some of the pictures, which is one of the newer methods of image classification designed for high resolution data. So these are looking at the spatial grouping of pixels with similar reflectance characteristics, and they can create polygon objects representing homogeneous areas. This allows for complex automated classification rules to be set based on both the spectral and the spatial properties of the data. Using this information, objects can be classified based on tone, texture, shape, and context. This allows for nested hierarchical classification from general to highly specific parts. So these are the steps that are used for object-oriented classification. One is segmentation of rasters into polygon objects, where these objects are defined such that they minimize within unit heterogeneity and maximize between unit heterogeneity. Then the user can control the scale parameter for acceptable level of heterogeneity, which can also control the degree to which segmentation is based on spectral or spatial characteristics. By repeating the segmentation with different scale parameters, the user can create a nested hierarchy of objects that is very much larger than the big objects. So here is an arc view. GIS being used. Photo of that same image that we had seen is taken, then it's being classified. You can see we have a mode, layer, image data, outlines. So we are going to draw a green as forest, yellow as impervious, and gray as fields. This is how to classify them based upon the objects. Then there are two levels of segmentation. You can see the same area is being segmented here. Multi-scale image segmentation, illustrated by two levels of segmentation. A very coarse one aiming at pastures and enclosures, the very fine one aiming at groups of shrubs. You can see that here. Group of shrubs, one aiming at pastures, one aiming at enclosures. Following the segmentation, each object is encoded with information about its tone, shape, area, context, neighbors, and spectral characteristics. Those are the mean, standard deviation, maximum, minimum, or this each band spectral reflectance. This information can be used for future extraction, in which objects' properties are analyzed to look for characteristics that help to discriminate one object type from another. You can see classification, differentiating one object and another. In this, by using supervised fuzzy classification, you can compare these two. Then the objects are classified by either by define the training areas of known cover, of supervised, or creating class descriptions organized through inheritance based rules into a knowledge base. It is known as the fuzzy knowledge base. Then object oriented classification steps. You can see right hand side, the options are given. In the knowledge base approach, complex membership functions can be derived that describe characteristics which are typical or atypical for certain classes. The more a given object displays the characteristics, the more likely it is to be classified into classes. The characteristics can be based on spectral response, summary statistics, shape characteristics, urgency, connectivity, and overlay. You can see the same picture which has been classified as forest, field, and remaining. Then we can classify this into further hierarchies of impervious as the forest as the forests into coniferous forests, deciduous forests, leafy forest, or oak forests. This is the class hierarchies. The classification can be hierarchical and nested, with final classifications with poorer ones. Small classified objects can be aggregated up to large object classes, and large objects can be split up into smaller ones. Then they can assign different segmentations to different class hierarchy levels, which allows for high precision classifications within coarser general classifications. You can see here the coniferous forests, then deciduous forests, beech, oak, impervious, and fields. So the object-oriented classification steps can use additional thematic layers to populate the knowledge base and create rules about what a certain class can be on top of it or near to it, which can increase the accuracy of classifications. However, training is required for the persons those are dealing with the object-oriented classification steps. For example, form fields will have a function of slopes, soils, etc. Different suburban development types such as functions of distance to urban centers, income, crime, etc. Here are some of the error evaluation schemes. How to fix an error in the pixel having a high fit for unstable and stable. Objects mean, standard deviation minimum and maximum is the given for recap steps. So then the object oriented classification software. So eCognition are the top object oriented classification software packages. If you have the original image like this, so that is converted to segment image like this, that is classified like this. So this is what characteristics of digital satellite image is. Any queries in this object oriented, you can type in chat box. If there are any queries, type in chat box, or else I'll proceed on to the next topic, which is the integration of remote sensing and GIS. Okay, since I couldn't find any queries in the chat box, I proceed on to the next topic of Unit 5, miscellaneous topics, integration of remote sensing, RS, and GIS, geographic information. So let us define this remote sensing. Remote sensing is what? Is this remote sensing principle is that it senses the useful information of any objects that is present on the earth. Okay, you can see that the different composite overlays, survey controlling soils, land cover, wetlands, floodplains, zoning, parcels, topographic bases. All these informations are being with respect to the earth. So that information is being acquired by remote sensing. Then it is given to GIS. So the GIS is a system that deals all types of geographic referenced data. So these two combinedly we are going to see in this topic. So the process of recording, measuring and interpreting images, digital representation of energy patterns that are derived from non-contact sensor systems is we call it as the main function of a remote sensing. And GIS is a system that is used to design, capture, store, manipulate, analyze, manage and present all types of geographic referenced data. So we have a real world, In the real world, there are different levels. You have buildings, you have water bodies, you have forests, you have mountains, you have elevations, you have streets, you have roads, you have aircraft lines, all those things. So from the real world, the land usage is segregated, water usage is segregated, the parcels is segregated, streets, customers are segregated. So which is the function of GIS, segregating them and analyzing it. So can you recall Google Earth? Information in the Google Earth is obtained through remote sensing, while its representation management on geographical locations is made possible only through GIS. We can only see through remote sensing the information whichever one we can see. For example, here is an Disney World, which is present in Florida, USA, where all the cartoons were initially started. The Mickey Mouse character, all the Disney characters started here. So surrounding that, these lakes are present, the street, the forest, streets, all are there. So the acquiring this information is only remote sensing, while representing them in different prospects according to the information available is called as GIS. Let's see. We had seen the history of remote sensing in our remote sensing topics. Just I'll give you a small hint of it. Remote sensing is what art or science of technology obtaining reliable information about the physical objects and the environment through the process of recording, measuring, interpreting, but without touching them. Is the same. The history starts with 1800 in the year. Discovery of infrared, followed by first photograph in 1826. Practice of photography came into effect in 1839, and photographs were taken from balloons during 1850s to 1860s. Then first aerial photograph from a balloon was taken. Infrared spectrum shown by scientists shared the properties of visible light. Theory of electromagnetic wave developed by James Clerk Maxwell came into existence. Then photography from airplanes were done during 1909. In World War One, the aerial reconnaissance was done from 1940 to 1918. The development and initial applications of aerial photography and photogrammetry during 1920 to 1930 were done. Then in the following 1929 to 1939, economic depression generated environmental crisis that led to governmental applications of aerial photography. Then during 1930 to 1940, development of radars in Germany, US and UK were done, where this development led into tragic wars, the World War II, applications of non-visible portions of electromagnetic spectrum, training of persons in acquisition and interpretation of air photos. In 1950 to 1960, military research and development was done. Then following that, the launch of satellite was a big breakthrough. Then 1970 to 1980, rapid advances in digital image processing was carried out. Then a new generation of Landsat sensors were deployed during 1980 to 1990. Then in 1986, Spot French Earth observation satellite was being launched. In 1980s, development of hyperspectral sensors, where we use the multi-spectral sensors. And in 1990s, global remote sensing and LiDARs were developed. So this is the picture of Joseph Neves, who developed New Texas radar. This is the first photo taken from balloon, 1858. First aerial photograph taken from airplane by Weber Wright of Italy. Early aerial photography by US Navy, 1914. His photograph illustrates difficulties encountered in early efforts to match the camera with the aeroplane. Then aerial photography during World War One, the crew of that. And aerial photography during World War Two, crew of that. You can see here cameras. All these are cameras which were used to take photographs of enemy countries. This is your modern day remote sensing using satellites, which we had discussed in our earlier classes also. The earlier pictures of satellites which took Saudi Arabia, Eastern India, the Bangladesh and Himalayas, the Gulf of California and Southern California, how it looked like. And photographs of the Earth taken from satellite when the satellite was revolving approximately 4 kilometers above, then approximately 1 kilometer above, which is picture number 2, which shows Russian Ulaanbaatar, Japan's Tokyo, Myanmar's Thailand's Bangkok, and Singapore. In 3, you can see aerial photograph. Sorry, in 3, you can see Landsat Aster photograph taken approximately 100 meters from the Earth. Then photograph 4 shows aerial photograph taken approximately 1 meter above. This is what we do in remote sensing. This is how we do or how we sense in remote sensing. So Earth's energy budget will look like this. So incoming solar energy is obtained from the sun, falls on the Earth's surface. 6% is reflected back by atmosphere, 20% by clouds, 4% by Earth's surface, 64% by clouds and atmosphere. Then another 6% is radiated directly to space from Earth. Out of that, radiation absorbed by atmosphere is 15% and carried out to clouds and atmosphere by latent heat in as water vapor by 23%. And 51% is absorbed by the land and oceans. So with that principle, the satellite will observe the signals which are being sent from the buildings. You can see here. Buildings, roads, soils, grass, water, forests, vegetation and all. So this is the same representation. So this is your active, this is your passive. So passive is your natural, which you are seeing in the desktop. So this is your passive, this is your active. Okay, which we have discussed in our unit number 1 and 2. The same is repeated here with an example of Landsat or spot in satellites or in space. Various steps in sequence. Energy source, then radiation and atmosphere, interaction with the target, recording of energy by the sensor, transmission, reception and processing, interpretation and analysis, then application. Now, we are going to combine this remote sensing and GIS. So all the sense data are given to an interpreter for making products to the specific users. GIS.
Yeah, go ahead.
The geographic information systems designed to capture, store, manipulate, analyze, manage and present all types of geographically referenced data. So these are computerized systems designed for storing, retrieval and analysis of geographic informations. This uses advanced analytical tools to explore at a scientific level the spatial relationships, patterns, process of cultural, biological, demographic, economic, geographic, and physical phenomena. Unique capabilities of the GIS is that it stores related geographic features in separate collections of files called map layers. These map layers can be reused easily and assembled into any number of map compositions and overlaid for analysis. The tools used are your known tools, the information which is acquired from remote sensing or geographic data from the satellite. Then hardware, computer, digitizer, scanner, printer, plotter. Software, your desktop GIS, internet GIS, CAD software, database software, or your GIS. Modeling depends upon the photos, videos, on the 3D models. GIS is that it gives answers to the following questions. Location, what is it? Where is it? What exact location it is? Condition, status of the futures, which location satisfies the given conditions. Trends, what changes occurred since the corresponding year or the corresponding date, which identifies geographic occurrence or trends that have changed or in the process of changing. Patterns, what spatial patterns exist, analyzes the spatial relationship between objects of geographic features. Modeling is that what if computers and displays an optimum path, a suitable and a land area or risky against disasters, etc. on a model, like how we search on Google Maps. So this is an example. This is how a basic data manipulation is done from remote sensing to GIS. This is one of the most common products of a GIS is a mapping. So the historical development of GIS, this has been evolved from centuries of map making and the compilation of spatial data, which was prepared by Eratosthenes, the Greek mathematician, astronomer, and geographer Eratosthenes, who laid the basic foundations for scientific cartography. Then Plotin's map of the world around AD 150, republished in 1492. Notice that the use of latitude and longitude lines and distinctive projection of the lines for mapping. In 1456, he completed a map of the known world in the 12th century, drawn with South Pole at top, such that he can easily invert it later. So the milestones of GIS are here. 1960 to 1975, pioneering of GIS took place. Individual personalities, important mainframe based systems were dominant. The era of innovation started from 1975 to 1980. Experiments and practice were done. Local experimentation, action, GIS, posting by national agencies, much duplication of effects. Then in 1980 to 2000, the commercial dominance, the era of commercialization took place. Increasing range of vendors, workstation and PCs becoming a common. Emergence of GIS consultancies. Then from 2000 onwards, the era of exploitation, where it is used for user dominance and vendor competitions. This data is taken from Haywood, which was published during 2004. Some of the applications of remote sensing and GIS: agriculture, forest, engineering, geology, land development, marine, disaster management, meteorology, water, environmental, national security, land use monitoring. So this is a Landsat image. An application of remote sensing which monitors the crop growth monitoring, vegetation monitoring. You can see that in different phases, the chronological cycles of crops from May, January, field preparation, February field, March field preparation, mid-March planting, April emergence, then slowly during May, emergence during June, square setting during July, blooming, during August, bowl setting during September, bowls opening defoliation, and during October it is the harvest. Then during November and December, discussing plowing again is being recycled. So this is for cotton. I am saying you this during the cotton. Cotton will be sowed during March, April, and it will be harvested during October, November. And so okay. So this this is how the fields will appear by the Landsat image. So how it will look like this. The field quarter, the field, agriculture field will look like this. Darker, darker, lighter, darker. Some greenish structures appears. Some green and orange. Green is being vanishing. Here greenish vanishing. Then here red, which shows that blooms setting. Then blooms opening defoliation in the harvest season. Similarly, you can see for sugar beets. Sugar beets field preparation starts during June, July. So June, July, the area of sugar beets will look like this greenish. Then planting like this. In emergence during October like this. So there it starts. Actual crop grows, thinning. Then during March or April it's ripening. Or during April it gets harvested. So this is for sugar beets. Similarly, you can see it for alfalfa flowers. So this is crop growth monitoring. The mode is 2003, which monitor the global normalized difference vegetation index. Shown, I've taken a photograph during this 2003, and it looked like this vegetation. And this remote sensing is used in forest monitoring also. You can see that mangrove forests will look like this at Borneo Islands. Montana forest will look like this. Here it is. Plantation or cropland is like this. Water is here. Degraded forest is like this. Lowland forest is like this. Peat forest is like this. Then urban heat island monitoring. Daytime and nighttime. This is a monitoring of island monitoring of the country Japan. Tokyo is taken during August 2007 and during nighttime and during daytime how it is. So land surface temperatures can be enhanced by land cover. Next is that the application of remote sensing is that it is used in wild fire monitoring. You can see that fires that occurred in Siberia, a close shot of that at a distance of 10 kilometer. Active burning spot is shown in red rectangles. Inside these are active burning in Siberian forest. Then the application of remote sensing in disaster management. You can see the Fukushima nuclear power plant, a GI. Before the Fukushima power plant got exploded, it was looking like this. You can see this before, and there is a yellow line below that. It is your after. So after the Fukushima nuclear power plant got exploded, disaster was occurred. You can see how this is looking. Then application of remote sensing in land users. So a Landsat composite image of the river near Newfoundland in Canada. So this is the place in Canada which is being taken. So when we zoom it using Landsat, it will show like this. Flow of a river. Then land use change. So 9 years of land cover change in Vietnam, how it is being done. Okay, the blue indicates your water, pink indicates your mixed forest, yellow indicates your croplands, green indicates your evergreen broadleaf forest. So in 1998, the vegetation was like this. You can see that these are the parts. In 1998, it was being classified like this. So when you see in compare, when you see in 2007, you see the same Vietnam, how it is. So the water resources has been depleted in 2007. The mixed forest got vanished. The mixed forest got vanished to a 4%. The evergreen broadleaf forests got vanished by 1%. And the croplands increased by 8%. You can see that. Within a 9 years of time. Then applications of remote sensing in water is that you can see two color, band 1 in blue, band 2 in green, band 3 in red, band 4 in near infrared, band 5 in short wave infrared, and the true color of water penetration inside the water. Then applications of remote sensing is flood mapping. You can see satellite image of St. Louis on July 4, 1988 during normal river level, which is left hand side. Then in July 18, 1993, St. Louis satellite image was taken, and you can see the height of the flooding. You can see the more blue indicates there is more flood. So within this, you can get data where there is high risk of flooding. Then remote sensing is used in military usage complexes. You can see that which can be hidden. Initially, all the remote sensing was being developed for military usage. You can see that before shrinks and after shrinks. Before the strike of an attack here, then after the strike of the attack here, how it has been demolished. Similarly, you can see here before the strike, after the strike, before the strike, after the strike. So here, the Republican Palace compound, military attack. So any queries, type in chat box.